Welcome back to Mechanical Engineering Made Simple. Today we're kicking off a 5-part series on fluid mechanics. School sells you smooth streamlines, but the real world says hold my beer. Stick around, this might save you from standing knee-deep in regret, wondering if the math lied or if the pipes are possessed. If you haven't already, hit like and follow, drop a comment if you enjoyed it.
Yeah, it is just a phenomenal topic to dive into. Fluid mechanics has this, infamous reputation across basically every engineering discipline for being just relentlessly unforgiving. I mean, nature simply does not grade on a curve.
Right, and we are setting up a true masterclass today. We want you, sitting there listening, to take a front row seat as we bridge that terrifying gap between the pristine theories you find in textbooks and the wildly unpredictable reality of how fluids actually behave inside pipes, pumps, and engines.
Oh, exactly.
We're going to decode the foundational characteristics, the physical laws, and the complex thermophysical properties that govern basically everything moving around us.
And that really is not an overstatement at all. Because if you are, say, designing municipal water infrastructure or engineering the next generation of jet turbines or, just trying to figure out why a high-rise HVA system sounds like a jet engine taking off, you are bound by these laws.
Yeah.
If your foundational assumptions are flawed from the start, your hardware will fail. Full stop.
Okay, let's unpack this. And let's bypass the elementary school definitions, right?
Yeah.
Because you and I know that a liquid changes shape to fit its container and a gas expands to fill a room. We do not need to rehash the absolute basics here.
Right.
What I want to dig into is this mathematical trap of the continuous isotropic substance.
Yeah.
Our sources just keep using this phrase over and over. But any basic chemistry class teaches us that fluids are not continuous.
No, not at all.
They're mostly empty space, right? Just populated by billions of individual molecules bouncing around in a microscopic void.
Yeah, and that is the core contradiction we really have to resolve before we can even write down our first equation. You are absolutely right about the void. Let us look at the air in the room you are sitting in right now.
Okay.
At normal room temperature and standard atmospheric pressure, those nitrogen and oxygen molecules are moving at incredible velocities, just colliding constantly.
Seeing absolute chaos.
Total chaos. But if you measure the average distance a single molecule travels before it smashes into another one, what physicists actually call the mean free path, it is roughly 0.06 micrometers.
Wait, 0.06 micrometers.
Exactly.
So we are talking about a scale so incredibly small, it is almost incomprehensible to the human brain.
It is entirely microscopic. And that unimaginably small distance is the exact reason we are allowed to pretend, for the sake of engineering, that fluids are a continuous, unbroken substance.
Because it just blurs together.
Right, because imagine trying to run the math for a trillion individually bouncing molecules inside, like a simple 1-inch water pipe.
The computing power required just to model a single glass of water would probably melt the world's most advanced supercomputers.
Oh, it absolutely would. So engineers use a macroscopic average, because free path is infinitesimally small compared to the physical size of the pipes, the turbine blades, or the airplane wings we are building. All that statistical static blurs into a smooth picture.
Oh, I see.
Yeah. We treat the fluid as a solid, continuous block of material that possesses uniform properties in all directions, and that is the isotropic part of the phrase.
But anytime we zoom out and average things like that, we create a trap. When does that smooth, continuous assumption actually break our machines in the real world? Because the textbooks hand you some very rigid rules of thumb.
They do. And the most dangerous rule of thumb, the one that honestly triggers catastrophic failures in the field, is the absolute categorization of compressibility.
How so?
Well, the academic baseline teaches that liquids are entirely incompressible, while gases must always be treated with highly complex compressible math.
Let me push back on that for a second, because that actually makes intuitive sense.
Huh?
Water does not squash. If you fill a syringe with water and put your thumb over the end, you cannot push the plunger down.
Right.
But if you fill it with air, you can push the plunger halfway down easily. So why is that textbook rule a trap?
It is a trap because incompressible is a relative term, not an absolute reality. Let us test that logic with liquids first.
Okay.
Yes. For your average municipal plumbing system, treating water as completely incompressible is perfectly fine. But let us say you are designing deep-sea hydraulics. Imagine a remotely operated vehicle, an ROV, working on a wellhead at the bottom of the Mariana Trench.
Wow. Okay. The pressure down there is what, like 1,000 times atmospheric pressure?
Roughly, yeah. And under that immense stress, we have to look at a property called the bulk modulus of elasticity. Water actually has a bulk modulus of about 2.2 gigapascals.
Meaning what, exactly?
It means if you squeeze it hard enough, it will yield.
Yeah.
At extreme depths or inside a 10,000 psi hydraulic actuator, the fluid actually shrinks by several percent.
Oh, wow. And if I am programming a robotic arm and my hydraulic fluid shrinks by 3%, my arm movement is suddenly going to fall short of its target.
Exactly. If you assume the hydraulic fluid is perfectly incompressible at extreme pressures, your volume calculations are completely fictitious.
So the robotic arm just misses the valve it was supposed to turn.
Right, or a deep-sea buoyancy tank fails to provide the correct lift. Compressibility must be accounted for when liquids are highly pressurized.
That makes a lot of sense for extreme environments. But what about the other side of the trap? Air is a gas. The molecules are incredibly far apart compared to a liquid.
Sure.
If I have a massive industrial fan pushing air through the ductwork of a 60-story skyscraper, that air has to compress as it hits resistance, right?
You would naturally assume so, yeah, but you have to look at the magnitude of the pressure change. This is the inverse trap.
Okay, lay it on me.
Compressible fluid dynamics requires mathematically grueling nonlinear equations. But if you are moving a gas at low speed specifically, anything below a Mach number of 0.3, which is roughly 100 meters per second, the kinetic energy of the flow is minuscule compared to the baseline atmospheric pressure.
So the fan is pushing, but it is barely altering the atmospheric baseline.
Precisely. In a standard building's HVAC system, the change in air density from the fan to the farthest vent is usually less than 5%.
Oh, wow.
Yeah, and mathematically, 5% is statistical noise. You can entirely ignore it. You can treat the air as if it were a heavy, incompressible liquid like water.
So if I try to use complex compressible gas equations to design a simple office ventilation system, I am literally just wasting days of computational time for absolutely zero gain in accuracy.
You are. And knowing when to apply the continuous assumption and when to ignore compressibility is what separates a theoretician from a working engineer.
Before we move on to friction, the source material explicitly talks about this concept of the perfect fluid, or the ideal fluid. It is defined as a fluid that has zero viscosity and zero compressibility. Why do universities spend thousands of hours and charge thousands in tuition teaching us about a ghost fluid that literally does not exist anywhere in the universe?
It is a frustrating rite of passage, honestly. When you are staring at an exam paper about a frictionless, perfect fluid, it feels completely disconnected from reality.
Very.
But the physics of fluid mechanics are overwhelmingly complex. If you attempt to solve a real-world problem involving viscosity, compressibility, sheet transfer, and chaotic turbulence all at the exact same time on day one, the math is basically unsolvable.
So we rely on the concept of the perfect fluid to sort of isolate the variables.
Exactly.
It's a mathematical sandbox. We remove the internal friction and the springiness of the fluid so we can just look at the raw mechanics of pressure and velocity.
That is a great way to put it. We use the Euler equations for the perfect fluid. Once you understand how that idealized baseline behaves, then we slowly add the real-world messy stuff like the Navier-Stokes equations back in.
Which brings us to the most critical, messy variable of them all.
Right.
Let's get into the internal friction of flow. Because now that we know fluids deform and flow, we have to talk about how they resist that deformation.
Yeah.
When I hear the word viscosity, I just think of the difference between pouring honey and pouring water. Honey is highly viscous, water is not. But mathematically, what is actually happening inside the pipe?
At a molecular level, viscosity is a fluid's resistance whenever two layers of that fluid slide over each other.
Okay, visualize that for me.
Visualize a deck of playing cards sitting on a table. If you press your hand flat on the top card and slide your hand forward, the top card moves the most.
Right, yeah.
The friction between the cards causes the card beneath it to move slightly less, and the one beneath that moves even less, until you reach the bottom card, which is stuck to the table and does not move at all.
And fluids do exactly the same thing.
They do. This brings us to Newton's law of viscosity. Sir Isaac Newton figured out that the shear stress, the actual mechanical force required to slide those layers, is directly proportional to the velocity gradient.
So if you want to force the fluid layers to slide over each other at a faster rate,
you have to apply exponentially more force. And the proportionality, a constant in that mathematical relationship, is what we define as the dynamic viscosity.
the sources bring up a specific analytical model called Couette flow to explain this.
Yes, Couette flow.
Two parallel plates, one fixed, one moving, with fluid between them, creating a linear velocity gradient. I have to be honest, it sounds incredibly abstract. Where does a parallel plate model ever actually exist in a piece of machinery?
It seems like a purely academic thought experiment until you apply it to a rotating shaft. Think of a massive drive shaft inside a stationary mechanical bearing, like the main rotor shaft of a power plant turbine.
Okay, so you have a spinning metal cylinder inside a stationary metal sleeve.
Yes. The gap between the spinning shaft and the stationary sleeve is unimaginably small, often just a fraction of a millimeter, and that gap is filled with a thin film of lubricating oil.
Right.
If you zoom in close enough on the curve of that massive shaft, the curvature becomes irrelevant. To the fluid trapped inside, those curved surfaces essentially look like two flat parallel plates.
Oh, I see. One plate is the stationary housing, and the other plate is the surface of the spinning shaft moving at a constant velocity.
That is hydrodynamic lubrication. The oil molecules stuck directly to the spinning shaft are moving at the exact speed of the shaft, and the oil molecules stuck to the stationary housing are not moving at all.
That's the no-slip condition, right?
Yes, exactly. The oil in between those two boundaries forms a steep velocity gradient.
The source material actually gives a brilliant real-world example of this. It outlines a cylinder with a diameter of 122 millimeters, spinning inside a concentric long pipe with a diameter of 125 millimeters.
Leaving a gap of just 1.5 millimeters all the way around. And that gap is flooded with oil. To figure out how much mechanical torque is required simply to overcome the resistance of the oil and keep that cylinder spinning at 1 meter per second, you have to calculate the shear stress of the oil layers sliding over each other.
That is Couette flow in action.
Yes. And it is critical because all of that friction generates heat. If an engineer underestimates the viscosity of that oil, the motor spinning the shaft will draw too much power, the friction will generate excessive heat, the oil will degrade, and the bearing will wipe itself out catastrophically.
Let me clarify something from the text here because it makes a hard distinction between dynamic viscosity and kinematic viscosity. What is the difference, and why do we need two different terms to describe fluid friction?
It really comes down to how we analyze forces. Dynamic viscosity, which is measured in Pascal seconds, is the absolute raw internal friction of the fluid.
Okay.
It is the actual physical force required to overcome the sliding layers we just talked about. Kinematic viscosity, on the other hand, is simply the dynamic viscosity divided by the density of the fluid.
So if dynamic is the raw stickiness, kinematic is the stickiness relative to the fluid's mass.
That is a really good way to conceptualize it. Kinematic viscosity tells you how the fluid's internal friction relates to its inertia.
Like when momentum is involved.
Exactly. It is incredibly important when you are calculating momentum diffusion, like trying to predict exactly when a smooth laminar flow will break down into chaotic turbulence. Dynamic viscosity is the force. Kinematic viscosity dictates how that force alters the fluid's motion when gravity or other inertial forces are in play.
That is a crucial distinction. Now let's get to the massive pain point for viscosity. The assumption that heat affects all fluids the exact same way.
Oh, this is a big one.
Because the intuition is simple. When you heat something up, it melts, it gets runnier. You heat up pancake syrup, it pours much faster.
That intuition holds true for liquids, yes. But if you apply that same logic to gases, you will design a system that fails immediately. This is the temperature paradox of viscosity.
Let's test that logic. Why does a liquid get thinner, less viscous when you heat it?
In a liquid, the molecules are packed very closely together. The dominant force creating the internal friction, the viscosity, is the intermolecular attraction.
The molecules just pulling on each other.
Right. The cohesive forces are literally holding the molecules together, fighting against the sliding motion. When you heat a liquid, you are pumping thermal energy into it. The molecules get excited, they move faster, and they physically separate slightly from each other.
And that tiny bit of distance breaks the cohesive bonds.
It severely weakens them, yeah. Because the attraction is reduced, the internal friction drops, the liquid gets thinner.
So syrup gets runny. But what happens to a gas? Because a gas is already spread out.
Exactly. In a gas, the molecules are so far apart that cohesive forces are basically non-existent. The viscosity in a gas does not come from molecules clinging to each other. It comes from molecules colliding with each other. The faster-moving layers of gas collide with the slower-moving layers, transferring momentum and slowing the whole system down.
Let me see if I can map this out with an analogy. A liquid is like a tense, incredibly packed dance floor.
Okay, I like that.
Everyone is shoulder to shoulder, holding on to each other. It is hard to move through. But if the DJ puts on a highly energetic song, adding heat, people loosen up, They create a bit of space, the tension drops, and suddenly you can slip through the crowd much easier. Viscosity goes down.
That illustrates the cohesive breakdown perfectly. And for the gas?
For the gas, well, if the molecules are already far apart, they aren't holding hands. It is more like an arena full of kids in bumper cars. There is plenty of space.
Right, they aren't touching.
But if you give those kids more energy, if you crank up the speed of the bumper cars, they start crashing into each other constantly. If I try to walk across that arena, all those high-speed collisions are going to impede my progress.
Yeah.
More energy means more crashes, which means more resistance.
That is the exact mechanism. When you heat a gas, the molecular movement becomes violently vigorous. They zip around much faster, drastically increasing the number of collisions between the sliding layers. That rapid momentum transfer acts like a physical brake on the flow. So when you heat a gas, its dynamic viscosity actually increases. It gets thicker and more resistant to flow.
That is wildly counterintuitive.
It really is. And if a mechanical engineer forgets that paradox, say, they're designing a high-temperature exhaust system for an industrial gas turbine, they might assume the hot exhaust gas will flow out easily simply because it is hot.
Oh, no.
Because of that assumption, they will drastically underestimate the frictional pressure drop in the exhaust duct. The turbine will experience back pressure, lose efficiency, and potentially stall.
A multi-million-dollar failure because someone saw gas behave like hot syrup.
Exactly.
That leads us perfectly into the next major concept. We know how fluids deform. We know how they resist. Now we have to look at the unbreakable laws that govern their energy when they are in motion.
We have to start with the absolute bedrock, the first law of thermodynamics. It is the conservation of energy. Energy cannot be created or destroyed. It can only be altered in form. But when we apply this law to a moving fluid, we cannot just look at a static block of material. We use what is called the steady flow energy equation.
The sources show a diagram for this, focusing on something called a control volume. Let's paint that picture for the listener. We're looking at a turbo machine, let's say an industrial pump or a turbine.
Visualize a defined boundary in space, like a black box. Fluid flows into the box at a steady mass rate through an inlet and flows out at the exact same steady mass rate through an outlet.
Okay.
Inside this black box, energy is constantly transferring and shifting forms.
So what kind of energy is moving around in there?
Several types. The fluid might be doing physical work on a spinning shaft, like steam spinning a turbine blade, which physically extracts energy out of the fluid.
Okay.
Or a spinning shaft might be doing work on the fluid, like a compressor packing air into a tight space, which adds energy. And simultaneously, there might be heat transferring in or out through the physical walls of our black box from the outside environment.
So the steady flow energy equation is just an accounting ledger.
Very much so.
The total energy of the fluid entering the box, plus any heat added from the outside, minus any mechanical work extracted by the shaft, must exactly equal the total energy of the fluid leaving the box.
It is the ultimate ledger. It accounts for the enthalpy of the fluid, which is a combination of its internal thermal energy and its pressure volume flow work. It accounts for its kinetic energy from its velocity and its potential energy from its physical elevation.
Wow.
If you are designing any piece of turbomachinery, this equation is your Bible.
But the steady flow equation is broad, right? It looks at the whole black box.
Yeah.
When we want to look at the fluid behavior microscopically along a single streamline, we use Bernoulli's equation.
Yes.
This is arguably the most famous equation in fluid mechanics, and it brings us to a concept that completely tripped me up: stagnation pressure.
Bernoulli's equation is essentially a simplified frictionless energy balance. It dictates that the total mechanical energy along a streamline in an ideal fluid remains absolutely constant. That energy exists in a delicate balance of three forms: static pressure, kinetic energy from velocity, and potential energy from elevation.
Let me dictate the math for stagnation pressure exactly as it is defined in the source text. P naught equals P plus 1/2 rho times C squared.
Let us dissect that. P naught is the stagnation pressure. It is the absolute maximum pressure you could possibly harvest from the fluid if you brought it to a complete dead stop with perfect efficiency.
Okay, so that's the max potential.
Right. P is the static pressure. That is the baseline pressure you would feel if you were floating alongside the fluid, moving at its exact same speed.
And the second half of the equation, the 1/2 rho times C squared term.
That represents the dynamic pressure. Rho is the density of the fluid, and C squared is its velocity squared. It is the kinetic energy of the flow converted into pressure terms.
So basically, the equation for stagnation pressure is simply stating, if I take the baseline static pressure and I violently convert all of the fluid's kinetic energy into pressure by slamming it into a wall. What is my total?
That is a very visceral but accurate way to say it.
Where do we actually use that in the real world?
It is critical for aviation. Think of a pitot tube jutting out of the nose of a commercial airliner. The air slams into the open tip of that tube and comes to a complete dead stop, creating stagnation pressure.
Oh, I've seen those.
The aircraft's computers measure that stagnation pressure, subtract the static pressure of the surrounding atmosphere, and use the difference to calculate exactly how fast the plane is flying.
Wow.
Yeah, and if that tube freezes over, the computers lose their velocity data, which has historically caused tragic aviation accidents.
Now, when we pivot to dealing with liquids, especially in massive systems like municipal water pumps or hydroelectric dams, the sources shift away from talking purely about pressure and introduce the concept of head. I will read the math for this one too. H equals Z plus P naught divided by rho times G.
Head is a wonderfully practical visual concept for engineers. It expresses the energy of the fluid not in invisible pascals of pressure, but in visible meters of elevation.
So like height.
It literally answers the question, if I tapped a vertical pipe into this system, how high could the fluid's current energy state push a column of itself straight up into the air?
Let's look at the terms. H is the total head. Z is the current physical elevation of the fluid above your baseline ground level.
Yes.
And the P naught divided by rho times G term basically converts the total stagnation pressure, which includes the static pressure and the velocity, into an equivalent height.
Yeah, it makes visualizing the workload of a pump much more intuitive. An industrial water pump does not just provide a certain pressure rating, it provides enough total energy to lift a heavy fluid a certain number of meters into the air, overcoming gravity and pipe friction along the way.
But this brings us to a massive pain point. Misapplying the Z's term, the elevation term, by blindly copying Bernoulli's equation without understanding context.
This happens all the time. Bernoulli's equation includes that Ziz term for gravitational potential energy. Now, if you are analyzing a liquid like water flowing down from a mountain reservoir to a hydroelectric turbine in the valley, that elevation Ziz term is everything.
Because it's falling.
Right. The massive weight of the water falling over a vertical drop is what physically powers the turbine. The head is the defining characteristic of the system.
Because water is incredibly heavy. The density is near 1,000 kilograms per cubic meter. But what happens if an engineer applies that exact same liquid mindset to a gas system? Say, a natural gas pipeline that goes up over a mountain pass and down the other side.
Gas is incredibly light. The density of air is roughly 1.2 kilograms per cubic meter. For gases or vapors, the change in gravitational potential, the Ziz term, is almost entirely negligible compared to the massive forces of static and dynamic pressure.
It's just not heavy enough to matter.
Exactly. The elevation term for a gas is statistical noise.
So if gravity exists, why can we just cross it out of the equation for a gas pipeline?
Because the effort required to push a feather up a hill is negligible compared to the effort required to overcome the aerodynamic friction of pushing it through a pipe.
Oh, that makes sense.
But engineers will sometimes tie themselves in absolute knots. They will try to calculate the exact elevation changes of a complex HVAC duct system running up a 50-story skyscraper, stressing over the elevation head.
Oh, no.
When in reality, the physical weight of the air inside the vertical duct is basically zero compared to the massive fan pressure required to move it.
So they overcomplicate gas pipelines by treating them like water pipes.
They do. And conversely, if you take gas logic where you safely ignore gravity and blindly apply it to liquid vertical pipes, you will end up specifying a water pump that cannot even push the fluid out of the basement. You have to know the physical mechanism behind the math so you know when it is safe to cross a term out.
That is a phenomenal reality check, which leads us to hardware. We have the equations, we know the laws. Let's look at the actual physical components where these equations make or break a design. What exactly is a diffuser?
At its simplest, a diffuser is a geometric component in a fluid flow system designed to reduce the flow velocity and, by slowing the fluid down, deliberately increase the static fluid pressure.
The sources mentioned that most turbomachinery flows are subsonic, meaning the Mach number is less than 1, so the fluid is moving slower than the speed of sound.
Correct.
And for subsonic flows, a diffuser is shaped as a channel that diverges in the direction of flow. It physically gets wider.
Yes. Think of a cone where the fluid enters the narrow end and exits the wide end. You will find them everywhere in high-performance engineering.
Like where?
Well, closed-circuit wind tunnels use massive diffusers to slow the air down after it passes the test section, so the air can be routed around the corners of the building without massive frictional losses.
The sources also mention a critical diffuser duct inside a gas turbine engine located right between the compressor and the burner. Why is it so crucial there?
A jet engine compressor relies on spinning blades to pack air into a tight space, which speeds the air up immensely. But if you try to inject jet fuel and ignite a flame in a hurricane-force wind, the flame will simply blow out.
Oh, obviously.
You need a diffuser to slow that high-velocity air down, recovering its static pressure so the flare can maintain a stable, continuous flame.
Okay, here's where it gets really interesting. My intuition is screaming that this is entirely backwards.
How so?
If a diffuser is just a diverging pipe, a pipe that gets wider, how on earth does making the pipe wider increase the pressure? Because everyday experience says that if I want to increase the pressure of water coming out of a garden hose, I squeeze the nozzle. I make the hole smaller, not wider. Why does the engineering textbook say I need to make the pipe wider to get high pressure?
It is the ultimate paradox that trips up almost every engineering student until they have that light bulb moment with Bernoulli's equation. Let us test that garden hose logic.
Okay, let's do it.
When you are holding that hose and you press your thumb over the nozzle, what are you actually doing to the water?
I am making the water shoot out much faster. It sprays further across the yard.
You are increasing the velocity. By restricting the physical area, the continuity equation demands that the fluid must speed up to force the same amount of mass through the smaller hole. So the kinetic energy of the water skyrockets.
Right.
But Bernoulli's principle tells us that the total energy must remain constant. If the kinetic energy goes way up, something else has to go way down to balance the ledger.
The static pressure.
Yes. When you squeeze the hose, the static pressure of the water at the exact point of the nozzle actually drops significantly.
But it feels like high pressure. It stings when it hits my hand.
Because you are not feeling static pressure. You are feeling dynamic pressure. When that high-velocity water hits the solid object of your hand, it comes to a dead stop. All of that massive kinetic energy violently converts back into stagnation pressure against your skin.
Ooh. So my thumb is a nozzle. It is converting the static pressure inside the hose into kinetic energy.
Precisely. A diffuser is the exact opposite of your thumb. Fluid enters the narrow end of the diffuser moving very fast. It has high kinetic energy but low static pressure.
Okay.
As the channel diverges and gets wider, the fluid is forced to slow down. The kinetic energy drops. And because energy must be conserved, that lost kinetic energy is converted directly back into static pressure. The fluid presses outward against the walls with much more force at the wide exit than it did at the narrow inlet.
So slowing it down is what builds the static pressure back up. That completely flips my intuition.
It does, and designing an efficient diffuser is one of the hardest geometric challenges in fluid mechanics because of a phenomenon called flow separation.
How does flow separation happen?
As the fluid moves through the widening diffuser, it is fighting an adverse pressure gradient. The static pressure is rising, pushing back against the flow.
Like a wall.
Sort of, yeah. The fluid right in the middle of the pipe has plenty of momentum to push through. But the fluid right next to the wall, the boundary layer, has lost a lot of its energy due to friction.
Right, from scraping against the pipe.
Exactly. If you make the cone diverge too quickly, if the angle is too steep, that slow-moving boundary layer runs out of kinetic energy, it stops, and the high pressure actually pushes it backwards.
The fluid rips away from the wall.
It separates, creating massive, chaotic, turbulent whirlpools called stalls. You lose all of that precious kinetic energy to heat and vibration instead of recovering it as static pressure.
That sounds bad.
Very bad. The source material provides performance charts for conical diffusers, showing how engineers have to carefully balance the length of the diffuser against the area ratio to avoid this catastrophic flow separation.
If you get the geometry wrong, the physics punish you immediately. Now, I want to pivot away from the idealized math and look at the raw data, the thermophysical reality check.
Let's do it.
We have spent this whole time discussing the perfect continuous isotropic substance. But what happens when we look at specific real-world chemicals?
This is where we leave the textbook's theory behind and enter the laboratory. The provided source material contains massive, dense thermophysical properties tables. We are talking pages and pages of empirical data mapped out across vast temperature and pressure ranges for various fluids.
They track everything: density, enthalpy, entropy, specific heat capacity at constant volume and constant pressure, the speed of sound in the fluid, thermal conductivity, surface tension.
Everything.
And when you look at drastically different fluids side by side, it is eye-opening. The sources highlight methane, water, and exotic refrigerants like R116, which is hexafluoroethane.
It is the ultimate reality check for an engineer. Let us look at the saturation lines, the boundary where a fluid boils from a liquid into a vapor. The swings in physical properties across that line are violent.
Give me an example.
Take liquid water. At standard conditions, we know its density is near 1,000 kilograms per cubic meter. But when it crosses that saturation line and flashes into steam at normal pressure, the density drops to a tiny fraction of that.
I'm looking at the data for methane here. At 100 Kelvin, liquid methane has a density of around 438 kilograms per cubic meter. But the saturated vapor at that exact same temperature has a density of just 0.67.
Right.
That is an explosive expansion.
And that phase change completely alters how the fluid interacts with heat and work. You cannot model that behavior with a simple ideal gas law like PV equals RT.
Why not?
The ideal gas equation is a wonderful tool for low pressures and high temperatures, far away from the saturation line. But when you are dealing with a dense fluid near its critical point where the physical distinction between liquid and gas starts to blur entirely, those simple equations fail miserably.
The intermolecular forces become chaotic. So how do engineers calculate anything accurately near the critical point if the simple math fails?
They have to rely on incredibly complex empirical models. The modern standard for defining these properties is calculating the dimensionless residual Helmholtz energy.
That sounds intimidating. How do we even get the data to build a Helmholtz energy equation?
It involves decades of meticulous laboratory experiments. Scientists have to place these chemicals, like hexafluoroethane, into highly controlled cryogenic chambers.
To measure what?
Well, to find the specific heat, they use highly insulated calorimeters, injecting precise amounts of thermal energy and measuring the exact temperature change. To find the speed of sound in a freezing gas at 180 Kelvin, they use acoustic resonance chambers, bouncing sound waves through the fluid at various pressures.
Wow.
They gather thousands of data points and fit them into massive, nonlinear equations with dozens of parameters. It is pure, heavy, empirical thermodynamics.
And this leads straight into the massive pain point for this session: the absolute disaster of treating thermophysical properties as fixed constants.
It is arguably one of the most dangerous things a thermal fluids engineer can do. In basic high school physics, you are taught that water has a specific heat capacity of 4.18 kilojoules per kilogram Kelvin. It is treated as a universal constant.
Right.
But look at the tables for these industrial fluids.
Okay, if I look at the isobaric specific heat capacity for methane vapor, it starts at 2.14 at 100 Kelvin, but as the temperature goes up to 190 Kelvin, it spikes to over 140.
The property swings wildly depending on the temperature and pressure. Thermal conductivity does the exact same thing.
So you can't just use one number.
No. If an engineer assumes that specific heat or thermal conductivity is a static number across a system that experiences large temperature swings like a heat exchanger in a power plant or an aerospace cooling loop, their heat transfer calculations will be entirely fictitious.
That's terrifying.
The system will either severely overheat and melt down, or it will be massively overdesigned and waste millions of dollars in excess material. You have to integrate the property changes across the entire temperature curve using those empirical tables.
It is a monument to human persistence. Someone had to meticulously measure all those properties just so someone else can design an efficient industrial freezer.
The tables in those appendices are the unsung heroes of the modern industrialized world. You cannot build modern society without them.
All right, to bring it all together, let us open the mailbag for our final segment. We are going to answer the most common questions people ask about fluid mechanics and thermodynamics, drawing directly from the principles we just broke down.
I am ready. What is the first question?
Question 1. Why are there so many different units for viscosity, and what is SI? It feels like every textbook uses a different letter or name.
It is a historical mess, honestly. Over the last century, different scientific disciplines developed their own systems in isolation. You have the absolute system, the MKS system, which is meter kilogram second, the CGS system, which is centimeter gram second, and finally the international system, or SI, which is what we are supposed to be unifying under today.
So what is the actual rigorous SI unit?
The standard SI unit for dynamic viscosity is Pascal seconds. It is clean, and it relates perfectly to the SI base units of force and area.
Okay.
But older texts and very specific industries like the petroleum and lubrication industries stubbornly cling to the CGS units, which are the poise and the centipoise.
Named after Poiseuille, right?
Yes, Jean-Léonard Marie Poiseau, a French physicist who did foundational work on fluid flow in human blood vessels. One poise is equal to 0.1 Pascal seconds.
Okay.
And pure water at room temperature happens to have a viscosity of almost exactly 1 centipoise, which makes it a very convenient reference point for chemists. So while Pascal seconds is the rigorous standard, poise and centipoise are deeply embedded in the engineering culture.
So you have to know both.
You have to be fluent in converting them, or you will be off by factors of 10 in your friction calculations, which will ruin your bearing designs.
Always check your units. Question 2. How much does specific gravity actually matter? And to frame this, the source material notes the specific gravity of seawater is 1.03 compared to pure water, which is exactly 1.
That is a brilliant question because a 3% difference sounds entirely trivial. If you are filling a backyard swimming pool, 1.03 does not matter. But fluid mechanics scales relentlessly with depth.
Why is it 1.03 in the first place? Why does seawater weigh more?
Because of the dissolved salts, sodium chloride, magnesium, calcium. These dissolved ions physically intercalate or fit into the interstitial microscopic spaces between the water molecules.
Oh, I see.
They add physical mass to the fluid without drastically increasing its overall volume, so the density rises.
Let us do the math for the submarine mentioned in the text. Diving to a depth of 6,500 meters.
Yeah.
That is deep ocean trench territory.
The formula for static pressure in a fluid column is density times gravity times height. If we assume the ocean was pure water, the density is 1,000 kilograms per cubic meter. Multiplied by 9.81 for gravity, multiplied by 6,500 meters of depth.
Well, wait, let me run that.
You get about 63.7 million pascals of crushing pressure.
Okay, 63.7 megapascals.
But it is seawater. The true density is 130 kilograms per cubic meter. Do that exact same math again with the true density, and the pressure is 65.6 million pascals.
That is a difference of almost 2 million pascals.
2 million pascals of extra crushing force on the titanium hull of that submarine simply because of a 3% difference in the density of the fluid.
Just from the salt.
If your structural engineer ignored that specific gravity because it seemed trivially small, the submarine implodes. At scale, tiny margins become catastrophic forces.
A sobering reality check. All right, final question for the mailbag. Question 3. How does surface tension actually work in the math? The sources give these great visual problems, like calculating the force needed to lift a fine wire ring off a water surface, or calculating the internal pressure of a tiny 1-millimeter bubble.
Surface tension goes right back to our discussion about cohesive forces.
Well,
Inside a bulk liquid, a water molecule is pulled equally in all directions by its neighboring water molecule.
bro, they all pull on each other.
The forces cancel out. But at the surface, where the water meets the air, the molecules do not have water above them. So the cohesive forces pull them laterally toward each other and downward into the bulk fluid, creating a tight, elastic, microscopic skin across the surface.
So when you try to lift a fine wire ring off the surface of water, you aren't just lifting the physical weight of the metal wire?
No, you are fighting adhesion and cohesion. The water molecules adhere to the metal wire, and their cohesive bonds hold tightly to the rest of the water surface.
Like breaking a rubber band.
Exactly. You literally have to exert a mechanical force to stretch and tear that microscopic, elastic skin. The math simply requires you to multiply the surface tension coefficient of the fluid by the total perimeter of the interface you are breaking.
And what about the bubble?
A bubble is fascinating. It is a sphere of gas trapped inside a very thin film of liquid. That liquid film has surface tension on both its inner and outer surfaces, and those cohesive forces are trying to shrink the bubble down to nothing, pulling inward.
So how does it stay a bubble?
To stop the bubble from collapsing, the gas pressure inside the bubble must be higher than the pressure outside.
What dictates that pressure?
The math is governed by the Laplace equation, which mathematically proves that the pressure difference is inversely proportional to the radius.
Meaning?
The smaller the bubble, the higher the internal pressure required to keep it inflated. A tiny 1-millimeter bubble actually has a significantly higher internal pressure than the surrounding water, just to fight off the surface tension trying to crush it.
It is amazing how much violence is happening at a microscopic scale just to maintain a simple, delicate bubble. We've covered the continuum assumption, The chaotic temperature paradox of viscosity, the unbreakable laws of thermodynamics, the mind-bending reality of diffusers, and the absolute necessity of empirical property tables. Do you have any final thoughts before we wrap up?
I want to leave you with a thought that brings us full circle to the very beginning. We just spent a massive amount of time discussing how to calculate the pressure on a deep-sea submarine, the flow through a jet engine diffuser, and the energy extracted by an industrial turbomachine.
Yeah.
And to do all of that, we had to rely entirely on treating fluids as a continuous, smooth block of material. We use elegant equations that assume a perfect, unbroken reality.
But we know the void exists.
It does. In reality, everything we just calculated is nothing more than the statistical average of billions of microscopic collisions happening in that void.
Right.
When a submarine hull withstands 65 million pascals of pressure, it is not being pushed by a solid wall of water. It is enduring an unrelenting, chaotic bombardment of individual water molecules. We build skyscrapers that withstand hurricanes, jet engines that cross oceans, and submarines that explore the abyss, all based on the statistical average of microscopic chaos.
It's just wild.
The math works, the engineering holds, but underneath it all is a storm of molecules that we simply choose to mathematically ignore.
That is a wild thing to think about next time you turn on a tap and watch the water flow out. It's just a statistically predictable riot. If you got something useful out of today's episode, hit follow and drop a like. It helps grow the show and keeps the engineering knowledge flowing.